All right, the next example we have is example 3, which is going to follow this from Mark 2. So what I'd like to do first is just to recap and relate it to something that you guys have already done, and that is with a one-dimensional parameterization, a path parameterization. So for instance, given some graph, let's say the graph of the quadratic, y equals x squared, for x between, let's say, -1 and 2. This graph can easily be parameterized in the following way. We can begin by saying let x equal t. Well, if x is t, this implies that y must be t squared. So this implies that our graph can be parameterized in the following way. R of t equals t comma t squared for t in our same domain as x, since x and t are equal. So that's a specific example. More generally, so for instance, given, let's say, y expressed as a function of x, you could parameterize this as saying r of t equals, let x equal t. We want our variable of the parameterization to coincide with the independent variable of our graph of that equation. So then this would be just f of t. So back over here, our function of x was x squared. So that's why this is a t squared. But even if we had something far more complicated, then whatever that thing is, just replace the x's with t's and use the same domain for x for t. So that's something you've seen and you've done a number of times. This remark number 2 is essentially saying the same thing. Now, if we have we still have a functional relationship, but our functional relationship is actually a function of 2 variables. Well, if we have 2 independent variables, then we're going to need a parameterization with 2 independent parameters, so u and v. Much like before, when we let x equal t, we're going to let x and y equal u and v. Then, once we have that replaced, we can just shove them in here and replace our function. So for instance, find a parameterization of the paraboloid given that. So using this example, we'll go ahead and just say r of u comma v equals u comma v comma u squared plus v squared. So that's one way to parameterize it. Specifically, it's using this idea up here in remark number 2. But this example 3 doesn't say to specifically use this method. And remember, for parameterizations, there's an infinite number of ways to parameterize anything. So this is not our only choice. This is a very easy and quick to write down choice. But sometimes, as we'll find out, this is not always the best choice for parameterizing something of this form. So let me just go ahead and call this option 1. And then option 2, we could look at the actual function that we have, x squared plus y squared, and notice that this is, whenever you see an x squared plus y squared, hopefully at this point you've trained yourself to think polar or cylindrical or whatever. Think about sine and cosine whenever you see something squared plus something else squared. So in this case, what we could do here is essentially we could go ahead and just say let r of u comma v equals, we could let x equal maybe v cosine u, let y equal v sine u. So think about that. If we go ahead and plug this in here, what do we get? Well, this would give us z equals v squared cosine u squared, or sorry, cosine squared u, plus v squared sine squared u. And of course, Pythagorean identity, we can factor out that v squared. The cosine squared plus sine squared just collapses into 1. So we get z equals v squared, and that tells us this would just be a v squared. So this is a very different way to parameterize it, but sometimes this makes certain integrals and things easier because we're exploiting the circular symmetry that the paraboloid exhibits. So for instance, if you think about what this looks like in sketching it, essentially right here in these two components, if we just look in these two components, so at any plane parallel to the xy plane, doesn't matter how high the plane is, just at all planes parallel to the xy plane, we are sketching a circle of radius v. That's exactly what's going on here. A circle of radius v, centered at the origins, being sketched. Well, with a paraboloid, of course, as you go up in z value, what happens to your cross-sectional circles? They get bigger. So that's exactly why, as z increases, our radius is going to increase. And then the relationship between the precise altitude, which is v squared, and the radius of our cross-sectional circles, we found that out just by doing this direct substitution and simplifying. So this one right here doesn't use any symmetry or anything. So one could expect that if you were to use this to calculate something more complicated like a double integral or something of that nature, it might lead to not as nice of a problem. The algebra might be harder. Anytime you exploit symmetry, you're almost guaranteed to get an easier result or a nicer result.